Security defines the boundaries. Architecture unlocks the possibilities. So how do you design a platform that operates within these constraints? It starts with a strong foundation. Custom-built infrastructure may look cheaper on paper, but in reality, it introduces considerable overheads, integrating components, keeping hardware and software aligned, and maintaining access to replacement parts. These factors quickly erode the initial cost savings. We needed an integrated platform that was proven to work as a unified system, not just a collection of parts. That's why we selected Fusion, an appliance optimized for OpenShift and built for resilience. The platform is supplied with redundancy across nodes, power, and storage, ensuring operations continue without interruption. Next, we considered implementation speed. Fusion provides an orchestrated install that streamlines provisioning and accelerates deployment, saving valuable time and reducing complexity. And, last but not least, it offers a unified view via the Fusion Management Console, a single pane of glass to manage the entire stack, reducing the operational burden. Fusion gave us a solid foundation. The next step was to acquire an OpenShift subscription for the platform. The platform was designed for Bare Metal OpenShift. This model simplifies licensing by covering the entire node, regardless of virtual CPUs. And the cost difference is dramatic. For example, with a 32-core node, license costs are reduced by 81%. Scale that up to 64 cores, and the savings are even greater. That means fewer licenses to manage, lower subscription costs, and a much better return on investment. But it isn't just about cost. Bare Metal provides more than a 10% boost in performance. With no hypervisor, workloads have direct access to the hardware, preserving valuable resources. The system feels immediate and fluid, delivering a responsive experience for developers and end users. So, when you combine the cost savings with the performance gain, the model was perfect. It also opened up new opportunities. OpenShift virtualization is only available on Bare Metal. This operator allowed us to convert virtual machines into containers and run them side by side with our modern workloads. Our approach followed 3 stages. We first evaluated applications by effort, risk, and impact to identify the best migration candidates. Next came a light-touch lift and shift migration. By running VMs natively on OpenShift, application teams kept their familiar processes and tooling, while we consolidated the underlying infrastructure. The migrated workloads could now be managed as code, with version-controlled configuration of resources and machine state, just like modern workloads. We then progressively refactored the applications into microservices. This phased approach simplified management, lowered operational cost, and enabled us to modernize at our own pace. Now, we turn our attention to the hardware, the compute that will power our workloads. A critical design decision we faced was compute configuration. The modern microservices architecture brings clear advantages, such as independent scaling and faster releases. But it also increases the resource footprint, separate runtimes, side processes, and additional management layers. All raise compute and memory requirements for the same function. The platform also had to support the entire software engineering delivery pipeline. This included every tool required to build, release, and maintain applications. To meet these demands, we needed a robust, resilient base of general-purpose compute. Should we deploy a dense setup with high-capacity nodes, or scale out with twice as many medium-sized nodes? Consider 4 nodes, each with 64 cores and a terabyte of RAM. Dense nodes like these deliver massive compute in a compact footprint. The trade-off? Less flexibility in workload distribution. And if one node fails, you immediately lose a large percentage of your cluster. Now consider doubling the cluster size and halving node resources to 32 cores and half a terabyte of RAM. This setup still supports large workloads, but it provides greater flexibility in balancing them across nodes. It also offers stronger resiliency. If one node fails, the others can absorb the load. That resiliency paid off when we experienced a hardware failure. Thanks to our scale-out configuration, operations continued without disruption. No downtime, no loss of capability. The system stayed fully operational until the replacement parts were sourced and fitted. Now, just one final consideration. If you leave nodes vacant for future expansion, remember that sourcing components late in the lifecycle may be constrained by part availability. Next, we added a GPU server to the cluster. This enables us to support workloads that were previously out of reach. And, in an air-gapped environment, those capabilities are even more valuable. Starting with accelerated workspaces. This means data scientists can iterate faster, experiment freely, and deliver insights all within a secure, reproducible container. It also enabled machine learning. We can leverage compute-intensive workloads, such as natural language processing and computer vision, that were previously impractical for us. And finally, everyone's favorite, generative AI. In most enterprises, this means cloud services. But, in defense, we simply cannot send our data outside the wire. By running models locally, we can explore cutting-edge AI applications. This lets us innovate without ever sacrificing security. Now that we've covered compute, let's talk about storage. Fusion supports a variety of storage options. Choose the most suitable option based on your storage and resiliency requirements. What I want to focus on is drive configuration. Imagine a cluster with 8 nodes. Depending on your needs, the minimum configuration will vary. For basic object storage, we only need 3 nodes. So let's add 10 flash drives to these storage nodes. But if you need advanced data protection, the minimum jumps to 6 nodes. Looks efficient, right? But here's where we ran into a problem. In our first deployment, we accepted the default minimum configuration, which consolidated storage onto the minimum set of nodes. On paper, it satisfied the requirement. But in practice, it created a critical point of failure. Regardless of which storage service you choose, I would recommend distributing storage across all nodes. Consolidating offers no benefit, and it undermines resilience. Balance is what keeps the platform stable. It's not just good practice, it's risk mitigation. No matter how resilient we make it, there is always the potential for a platform-wide issue. That's why external storage is critical. It's our safety net. We selected the IBM Flash system to safeguard our application backups and logs. We utilized the Fusion Backup and Restore service for namespaces and Loki for cluster logs. The storage array is equipped with high-performance flash storage that is on par with the integrated Fusion storage. And importantly, the device is fully encrypted, so the information remains protected at rest. In short, external storage isn't optional. It completes the resiliency strategy. So if problems occur, we have a secure, high-performance recovery path. Now, with the storage locked in, we shift our focus to networking. Planning is critical. Even minor oversights can lead to issues down the line. Taking the time to perform detailed validation will help avoid costly delays. Fusion recommends default network ranges for the pod, service, and storage networks. But you need to ensure that these are sized to suit your workload requirements. For example, the pod network directly limits the number of concurrent pods. You also need to ensure that any external-facing ranges do not overlap with enterprise networks. Otherwise, you'll run into routing conflicts and connectivity issues. Just remember, updating network ranges requires a full reinstall. Don't ask how I know. Next is throughput. Fusion supports a pair of 100 gigabit links on each of the high-speed switches. However, your data center may only support 40, 25, or even 10 gigabit links. That's where splitter cables, transceivers, and adapters come in. They help you match port speeds, connect reliably, and maximize cluster throughput. Regardless of your final configuration, ensure you use all 4 ports if possible. It's the best option for maximum redundancy. Then there's data center patching work. Something easy to miss, so line this up early. We had to fit a patch panel into the top 2 rack units, which required equipment and coordination with external service providers. And finally, compliance. Your data center may standardize on switch vendors, meaning Fusion's integrated switches may not align. We had to route them through in-pattern switches to stay aligned with enterprise standards. So make sure you confirm switch suitability early. This slide is the most important of the deployment story. In a fully disconnected environment, success depends entirely on having the right local services in place. Without them, the cluster simply cannot function. First, we needed a mirror registry. Not just for installation, it's a critical service for ongoing operations. In an air-gapped environment, every image must be staged locally. Treat the registry as a first-class service, not an afterthought. Alongside it, we hosted a private Git server for our source code and configuration repositories. Together, they form the backbone of our disconnected workflow. Critically, this server also functioned as an administration node. It gave us a control point to initialize, patch, and manage the platform. And when incidents occurred, it serves as the primary hub for connecting to hardware and running diagnostics. When we deployed Fusion, it only supported block and file storage natively. To bridge the gap, we installed MinIO on the registry server. This service presents block storage as the S3-compliant object storage that modern workloads expect. To complete the solution, we connected the storage array to the registry server via a pair of high-speed fiber-channel cards. And finally, this server also enabled us to validate the air-gapped deployment. To achieve this, we added the core services every cluster relies on: DNS, DHCP, and NTP, all hosted locally on the registry server. This standalone network enabled the project team to complete the install before it ever touched the enterprise network. Together, the registry server formed the backbone of our air-gapped platform, enabling administration, independent deployment, object storage, and secure delivery of artifacts and code. All these decisions came together to form a complete solution that delivers performance, resilience, and security. Bare Metal OpenShift scale-out compute with acceleration, resilient storage on and off the cluster, and a secure private registry. This platform supports everything from software engineering to advanced analytics and emerging workloads.